So welcome back. So we'll be starting with a new model today. So it is called as transmission lines. Okay. So very interesting and beautiful topic. And whatever you have learned so far will break down into pieces in this topic actually. So why am I saying that? That you will come to know by the end of this lecture. So let's start about it. So first thing obviously is what are transmission lines? So as the name suggests, they are used for transmitting something. And what is that something? It should obviously be power, right? Because we are from electronics and telecommunication or electronics domain. So what we want to transfer is nothing but power, right? So what are used to transfer power? Can you think of? So first thing which everybody might say and I assume is copper wires, right? So the second thing which you might suggest is what it will be? Twisted pair cables. Next you might say is TV cable. To be precise, it is a coaxial cable. The next thing you might say is optic fiber cable. So we have four types of cables. So what they are used, what is the common thing in them? They are used to transmit energy or power, as we say, from a point to the other point. So these are nothing but our transmission lines. Okay. So all these are transmission lines. So you might say you should have a doubt actually. So why we have different types of transmission lines? The reason is very simple. Because they are used for different applications. Okay. And the actual reason is because they are used at different frequencies. Okay. And that is the reason they are used for different applications. So what are copper wires used for? To transfer actual power, right? So they are used at a frequency of 50 Hz, as everyone knows. So twisted pair wires are something like this. So they are in the form of, the wires are actually twisted. That's why the name twisted power cables. So if you have a telephone at home, you will have this cable, right? So they are used in the range of, so they are basically used to transfer audio. So their range is around 8 kilohertz to 20 kilohertz, right? So a bit higher frequency. Then TV cable. So they are nothing but coaxial cables. They are used from around 80 to 120 megahertz, right? So these are all approximate values. So these are not absolute values, remember. So next are optical fiber cables. They are used for what? To send our internet data, to transfer information at a very high speed, right? At least theoretically they are used, right? So these are used at what frequency? Not even gigahertz, they are used in terahertz range, right? So what we observe, the frequency is increasing, right? But the underlying device is same. They may be in different forms, but they are all what? Transmission lines. Okay. So the underlying working of them is same, only what thing is changing is frequency, right? So far you might have got an idea that in electromagnetics what we are studying is mainly high frequencies, right? So what happens at high frequencies for a transmission line, that's what we are interested in. Okay. So let's start about it. So let's take a very simple network. So let's say I have a AC source. For simplicity, I'll take a DC source, and I have a resistor connected here. Okay. So this is V, and this is I. So I ask you to analyze this line or this network. So this is nothing but copper wire, right? So it is a transmission line. So if I ask you to analyze this, or what we'll do, we'll apply KVL, you will find the current. So what will be the current? What will be the current? So it will be simple. So this is the current I. So everyone will tell me, hopefully, that it will be by Ohm's law V by R. So this is one method. What is the other method to get the current? You can apply KVL. So you will apply KVL. So what will you get? So you can apply KVL in a loop only. So it will be plus V. What is the drop here? You will see 0. So minus 0. Minus what is the drop here? I into R. Summation of V plus summation of IR equal to 0. What is the drop here? Again 0. And this should be equal to 0. So therefore V equal to IR. So I equal to V by R. Right? So you have got the current. So everyone is happy. We can live a happy life thereafter, and we can leave, and we can close the course. Right? But that is not the end of the story. So let's say I give you an same circuit, okay? But what I am doing is, now I am using a AC source, okay? So before that, just to avoid confusion, what I'll do is, the same thing can be applied to AC source, right? Will your answer change that if this is V, this is R, and the current I is flowing? You will still say I equal to V by R, and you will still apply KVL using the same equation, minus IR minus 0 equal to 0. So therefore V equal to IR, therefore I equal to V by R. So again everyone is happy, right? So since this is the AC source, let me take the signal. So it will be somewhat like this, sinusoidal signal, right? And let me take the voltage at a particular instant of time, right? So it is dependent on time, right? This is time, and this is my voltage axis, y versus x, voltage versus time. So let's say I am at location AA prime on the transmission line, okay? So and this, at this voltage, at this location, the voltage corresponds to a point P at time t1. So I am at time t1. So this voltage value is P. Fine. So again I am repeating, I have a network with a AC voltage source. So since it is a AC voltage source, the voltage is sinusoidally changing with respect to time. So it has some frequency obviously. So what I am assuming is I am at a location AA prime along the transmission line at some distance from the voltage source, I can see. And at time t1 I am measuring the voltage. So at time t1 on the x-axis I am getting a voltage, let's say P, corresponding on the y-axis, okay? So next what I do is I measure the voltage at a different location, which is BB prime, right? And obviously at a different time, okay? And let's say the time difference is delta t. After a time delta t I am measuring the voltage, okay? So since I am measuring the voltage after a time delta t, right? So it will be somewhere, let's say this is delta t, right? So I am somewhere over here, right? So after a time t1 plus delta t, so basically what will happen, the voltage at A prime will take a finite amount of time to travel, since no signal can travel with infinite velocity, right? And we know the maximum velocity which we have seen so far is 3 into 10 raised to 8 meters per second. So nothing we can travel with infinite velocity, right? Maximum is speed of light, at least practically, right? So the voltage at AA prime requires some finite time to travel from AA prime to BB prime, right? So what will happen is, when the voltage at AA prime goes to BB prime, so at BB prime I will get the value as P volts, right? But the source is on, it is continuously giving us sinusoidal voltage. So what will happen to the voltage at AA prime when the voltage at BB prime is P volts? It will obviously change, right? So let's say it is something Q volts, right? So what is happening at AA prime at the time t1, I have a voltage of P volts. So then after a time delta t, so at the total time t1 plus delta t at BB prime, the voltage takes a finite time to travel from A prime to BB prime. So this voltage is P volts. So what is happening? What is the voltage at T1 plus delta T at A prime? This is a graph of voltage at A prime. Okay. So what is happening at T1 plus delta T? The voltage has changed to something Q volts, right? Means what is happening? The voltage at A prime is something Q, and at BB prime it is P volts, right? So there is a potential difference between these two locations, right? So if I try to apply KVL now, what will happen? Again, I'll have the voltage V. Initially we said this voltage was, there was no voltage here, so we wrote it as 0, but now there is some potential difference, so we cannot say it is 0. Let's say that potential difference, I write it as X, so I get V minus X. Then what is the drop here? Same as before, so higher. So similarly, since there is drop here, so I can have drop here also. So this will be, let's say, same or different. So let's say Y. So I am done with the loop. So it is 0, right? So can you find I here? You cannot find, because you don't know the voltages X and Y. That is the problem, right? So this is creating a problem for us, right? So this was the time in between, right? So this is called as the transit time, right? So I mentioned about velocity, so it is given as L by V. So velocity is distance upon time, right? So next, let's say I have this sort of signal, okay? So what is happening? Because of this drop which is generated, even though this is not having any element in between, I cannot apply KVL, right? So KVL in short is failing here. So as I said at the start of the lecture, your previous notions of the your notions of the previous subjects will break down like 9 pins here. So that is what is happening. I cannot apply KVL to this network. I have proved it. How I have proved it? I basically said that at the location A prime at time T1, the voltage is P volts initially. Then after a time delta T, so it will take a finite amount of time to travel from A prime to BB prime. So at BB prime, the voltage is now P volts. But what will happen to A prime? Since it is a different time, to be precise, T1 plus delta T. So the voltage will change here. So from P, it will go to Q volts, right? So there is a potential difference along this line also. So that is what we have considered here, X. Similarly, there will be a potential difference along this bottom line. So that will be Y. So because of this, I cannot find current because I don't know X and Y, right? So that is the problem here, okay? So let's say this was the signal before. Now I use this signal, okay? It is exactly same, only the time axis is changed, okay? We assume the amplitude is same, okay? So what will happen? What was the difference here? Let me take a different pen. So what was the difference here? I extrapolate this point here. I extrapolate this point here. So what is happening here? The difference is small, right? So it is small difference here. What is the difference here? It is very high, right? So what I can say? I can ignore this X and Y values since they are very small for this signal. So for this signal I can ignore, but I cannot ignore for this signal, right? That is what we try to understand from this diagram. Let me draw one more diagram. Let's say I have the signal which is somewhat like this now. So what will happen? Again, I will extrapolate it here. So what is happening? Again, I am getting a huge difference. This is a huge difference, right? So I cannot ignore it here. So what we can conclude from this understanding? So for this signal, I can ignore. For this, you cannot ignore, right? So this is which type of signal? So this is time axis, this is time axis, this is which signal? High frequency signal. And this is a low frequency signal. Means what I can say, for low frequency signals, I can ignore the effect. I talked about effect. So since the voltage at A prime takes a finite amount of time to travel from A prime to BB prime, so it requires a time to transit. So it is called as transit time effect. So this effect which we studied, that we cannot apply KVL, and if you cannot apply KVL, obviously you cannot apply KCL. So the where the laws fails, so that effect is called as transit time effect. Okay. So when to ignore this effect? When the frequency is very low. For example, this frequency, we can ignore this effect. So for this, we can ignore. Right. So for high frequency, we cannot ignore. Cannot. Right. Why we cannot ignore for high frequencies? Again, because you see a huge potential difference between the 2 points. For low frequencies, you don't see any potential difference. You see a very minuscule potential difference. So that can be ignored. Okay. So that is the reason this is the reason you are applying KVL and KCL so far for every subject. So even if you were designing a transistor HIE, HFE, etc., IV is VO upon VI, you always applied KVL and KCL, right? Because you are assuming that it is a low frequency signal. Okay, but this is not the only case. If you see this expression, it is what TR equal to L by V, right? So when is the transit time high? So if I say that the transit time is high, so this was delta T, right? So if I increase delta T, let's say this delta T is still here. So what is happening? Again, I am getting a huge difference, right? So this is a positive voltage, this is a negative voltage. So this is a huge difference, right? So if the transit time is high, means what? This length has to be high, L. When will this transit time will be high? When L is high. What is L? The length of the transmission line. So if length of the transmission line is high, then also I cannot ignore this. Then also I have to take this effect into consideration, right? So what is happening basically? Okay, I took the same page again, not an issue. So we have studied very important and very different, which you have studied for the past 3 years. Not even 3 years, 4 5 years I can say, because from 11th and 12th standard itself you are studying KVL and KCL. Okay. So what we have said, I cannot, even if it is a DC, so okay, I will not talk about DC source to avoid confusion. So what we said, that because of transit time effect, we cannot apply KVL and KCL to which signals? For high frequency signals and for signals which have length which is very high. Okay. So which are high frequency signals? All the telecommunication signals are high frequency signals, right? They work in the range of gigahertz, 2G, 3G, 4G, etc., right? So you cannot apply there. So we also saw optical fiber. So again, it is what? Terahertz, high frequency signal. So we now cannot apply KVL, KCL, etc. to analyze here, right? So here is the length high. Or simple copper wire, they are used to carry power from one point to other point. So they will travel huge amount of kilometers, right? So tens to hundreds of kilometers they will travel. So in this case, the length is very high, even though the frequency is low, remember 50 hertz, but the length is very high. So again, we cannot ignore this effect. So in both these cases, we have to take into consideration this effect. So if you are taking into consideration this effect, means what? KVL fails, and obviously KCL will fail if KVL is failing, right? So this is a very important thing. So it may be hard for you to digest, but just think over it. What is happening again? At the location A prime at time t1, I have a voltage of P volts. After a time, it will take a finite amount of time to travel from A prime to B prime. So here the voltage is P volts. But what will happen by this time when it travels till here? At T1 plus delta T it is, right? So at this point it will become something else. Let's say Q volts. Means there is a potential difference between these 2 points. From this you get this X term. Means you cannot find the current. Means KVL and KCL is failing. So this is what? Transit time effect, right? And from these diagrams we saw that it is applicable at high frequency, and since the transit time is L by V, if delta T is high, means the transit time is high, the length should be high. So if length is high, then also we cannot ignore this effect. So this is the very important concept and the crux of this module, which is transmission lines, which you need to understand. Okay. So what is happening now? Since we are not able to find X and Y because of transit time effect, we are not able to analyze this circuit, right? because our KVL and KCL is what we have used since 11th and 12th standard, and in BEE then circuit theory and networks, whichever was the subject in second year, right? So we need to take some other method, take recourse to some other method. So the circuit theory is failing. So if you have heard of, the solution is wave theory, okay, and that is what we have covered in the first 3-4 modules, okay. But what is the problem with wave theory? That you have seen, you have to deal with vectors. Why? Because you have fields there in waves, because the waves are traveling, they are traveling from one point to other, so magnitude as well as direction comes into picture, right? So wave theory is very tedious, so many people don't want this, right? So we need to have some, what do we say, trade-off between the circuit theory and wave theory, okay. So what is that trade-off we need to study, okay. So I think we'll stop here. So with this point, I'll not go further purposely because I want you to digest this fact that in this circuit, if it is a high frequency circuit, again I am stressing on that point, if it is a high frequency circuit, KVL or KCL fails, or if L is high, again KVL KCL fails. Why? Because of transit time effect, okay. So we are not able to analyze this, so we have to go to wave theory. But wave theory is tedious because it involves vectors, divergence, curl, del dot A vector, del dot D vector, etc, etc. So what we need to have some other method, okay. So before stopping, I'll just give a hint. So what we know is that KVL KCL can be applied for where the drop is not there, right? So what we can do, we try to divide this into very small sections. So usually we have seen in wave theory that the power travels along the z-axis. So in the same way, that's why we'll say this small section of the transmission line will take, and we'll assume it is delta z, right? And this section is so small that this drop can be ignored. So these both go to 0. So because of that, what will happen? You can apply KVL. Remember, only for this small section of a transmission line. So since you can apply KVL there, right? So you can analyze that small section, right? So whatever is true for that section will be true for each and every section. So you can then take the summation and you will get the solution, right? So this is just the crude idea of what we will be doing tomorrow, okay. So we'll stop here.